Hi everybody, welcome to General Physics 2. This is your first lecture video for chapter 16, which will be the first topic we're going to talk about. And Physics 2 is all about electricity and magnetism. And so the first thing we're going to talk about is electrostatics. So electrostatics means we are looking at matter with properties of charge and how they behave when they are still, okay, when they are static. So in this chapter, we're going to focus on the property of electric charge, the forces that occur between charges, and the electric fields that are produced by charges. So this is a breakdown of the sections in this chapter. There's 7 sections, and we're going to be going over all of them. Not all at once. This video, I'm probably just going to get up to section 4. A lot of these sections are really short. They're just brief introductions. So if it looks like a lot, don't freak out too much. It's not really that much content. It's a bit wordy. Okay, you'll find this textbook a bit wordy, and these slides are taken from the textbook publisher, which I have altered and reduced down somewhat. Believe it or not, I have reduced these down and edited them, but you'll see that they are a bit wordy. So I don't want you to, when you open up this slide deck and see 167 slides, don't freak out. It's not like you have to memorize 167 slides. There's just a lot of expansion going on, and it's kind of like reading the book in slide format. So we're going to go over the first 4 sections, and we're going to talk about this property of matter, which is called charge. And you may already have some intuition about charge. You may have used the word charge in your everyday language, like if you are charged up, right? That means you're like excited. And that, there is a reason that became a colloquial word, and that's because it has, an analogy in physics. And so we'll talk more about that. So you may already have a intuition about some of these things, and you'll see how we define them with physics. So in each of these chapters, this very wordy deck of slides, okay, there's another section, which are your goals, your learning goals for this chapter. So this is a good place to go back to when you're studying and to make sure that you can hit these goals after we're done, doing all the homework, doing the pre-lecture videos, okay? So, and then finally, in this kind of preamble to the chapter, this is going to let you know what kind of topics you need to have a good understanding of to be able to move forward in this chapter, okay? So the most important thing in this chapter, and the hardest part of this chapter, is going to be using vectors, okay? So I want you to think back on everything you know about vectors and try to recall it. And I'm just going to jump into it once we get to these types of problems. But if you need a refresher, I can point you to some examples and some exercises that will help you refresh your memory about using vectors. So, but for now, for most of this video, we're going to be talking qualitatively and conceptually about these things, about the things I'm going to introduce to you. Okay, and so the first thing we're going to talk about is this property called electric charge, okay? So matter, things that contain mass, right? Things that we can touch and hold, they have a property called electric charge. Okay, so in addition to mass, there's another property, it's called electric charge. And electric charge can be positive or negative. We're going to go back to figure 16.2. So electric charge can be positive or negative, okay? When something has a net electric charge, so meaning it has more positive charges than negative or more negative charges than positive, we say that that object is charged, okay? And any piece of material or matter that has equal amounts of negative and positive charge, that's a neutral object. So electric charge is a property of matter, but what makes up matter? It's atoms, right? Atoms make up matter. And the property of charge comes from atoms, and that's because the charged objects in the atom are the electrons and the protons, okay? And then we have these gray guys, which are neutrons, and the reason they are neutrons is because they are neutral. So neutrons don't have a charge. Electrons have a negative charge, and protons have a positive charge. You may have already known this from chemistry, right? So here's that figure I was going to go back to. Charge can be transferred between objects. And there's a couple of different ways we can transfer charge. The one we'll talk about right now is through friction, okay? So you may have seen this example done if you've taken physics previously, or if you have watched physics videos, an introduction to electrostatics. It's a very classic, very canonical example where you have a rubber rod and a glass rod, okay? And you take a certain piece of material that matches up with the material of the rod, and you rub that material on the rod, and what happens is you get charge transfer, okay? And so you'll notice we're talking about different materials. We have rubber rod with rubbing it with a piece of fur. You have a glass rod and you're rubbing it with silk. And so the reason why these combinations need to happen is because of their electronegativity. So when you rub these two materials together, what's happening is electrons are moving from one material to another. The material that is the most electronegative will be attracting the electrons, and the material that is the least electronegative will be giving up the electrons, okay? And so that's why particular combinations of materials must be put together, because if you need their electronegativity to be far apart from each other in order to get this transfer to occur. If they're too close to each other, it's going to be kind of like a moot point. You know, you're not really going to get electrons moving around. And so this demonstration, so let's say I have a rubber rod, rub it with fur, I have glass rod, rub it with silk. After the rubbing happens, okay, electrons have left the fur and gone to the rubber rod. And in the situation with the glass rod and the silk, electrons have left the glass rod and gone to the silk. So what's left over on the rubber rod is a bunch of electrons sitting on the surface. What's left over on the glass rod is a bunch of positive charges sitting on the surface. Why? Because the negative charges left and went to the silk. And so now we can demonstrate what I'm trying to demonstrate to you. So there's a little bit of a preamble here. So when you bring negatively charged objects together, okay, two negatively charged objects together, look at those force vectors. They point away from each other. There is a force of repulsion, okay? When you bring two positively charged objects together, you get also repulsion, okay? They repel each other. Now, when you bring a negatively charged object close to a positively charged object, you get a force of attraction, okay? That is the observation that we're making. Like charges repel, opposites attract, okay? And we've demonstrated that to you by also showing you that charge can be transferred. So it was a kind of a 2-for-1 there. So, oh, here we go. That's what we were just talking about, right? Our fourth demonstration, our fourth observation, if you will, is that electrically charged objects exert forces on one another, okay? And we just explained what those forces were. Opposites attract, okay? Opposites attract, like, same signs, repel, okay? And that force that of the attraction and the force of that repulsion is a special force that we call an electric force. So finally, the fifth observation here that all these experiments have shown us, the experiments that have been performed over the past, 400 years, is also that charge is never created or destroyed. So anytime that we are, vigorously rubbing these rods, okay, we are only moving charges around, specifically electrons, okay? We're moving charges around. They are not disappearing to another universe. They are not appearing from another dimension, okay? They're just simply being moved around. Every charge that has ever existed in our universe today has always been there. And that's where you may have heard this phrase that, we're all made of star stuff, right? Every charge that exists in anything in the observable universe, planets, stars, distant galaxies, every atom in all of those heavenly bodies have been there since we've known how to think about these things, okay? So, there's been supernovas, there's been the end of whole universes and the birth of a new galaxy and so on and so forth. We are all made up of those same atoms, recycled over and over, from the beginning of the universe. So charge is never created, it's never destroyed, it's always been present. So let's talk about another kind of cute and fun demonstration of this property that electrons are just simply able to move around from one object to another, okay? That opposite charges attract and like charges repel. This is another demonstration of that. So we've all done this before. You take a balloon, okay, a rubber balloon, and you rub it on hair or fur. And when you pull that balloon away from your hair or fur, in this case, what you notice is that your hair sticks to the balloon, okay? So what's going on when this happens? Well, when you rub your hair on the balloon, what you have done is allowed negative charges to build up on the surface of the balloon, okay? And the question is, well, your hair, what's happened to your hair? Well, your hair is made up of molecules, and those molecules can be polarized. So you may remember the concept of polarization from chemistry. And when something is polarized, it means that the positive side of the molecule points in one direction and the negative side of the molecule points in the other direction, right? And so if you bring a balloon that has a bunch of excess negative charges on it near a molecule that is polarizable, well, that molecule is going to rotate around so that the positive side is attracted, right? Because it's attracted to the negative side, it's going to point itself to be close to it. And the negative side of the molecule is going to want to be, pointing away from the negative charges because they have that force of repulsion. And so there you go. That's how your hair sticks to the balloon. So now let's get a little quantitative, okay? Let's talk about charge. So the unit of charge is the coulomb, okay? So that is the unit of charge. It's named after a French physicist who uncovered the fundamental law that governs the interaction of charges, okay? Basically the fact that opposites attract and like repel. So electrons and protons, you may also recall this from chemistry, they have the same magnitude of charge. Okay, and that magnitude is E, and numerically that is 1.602 times 10 to the minus 19 coulombs, okay? So protons would have a positive value of E, Electrons would have a negative value of E. To talk about charge in general, okay, so multiples of E's, all right, we're going to use the symbol Q. And so therefore, you can see that the Q of a proton is positive E, Q of an electron is negative E. So interestingly enough, another really cool fact about charges is that E is the smallest possible division of charge. There is no particle ever observed that has a charge smaller than 1.602 times 10 to the minus 19 coulombs. Everything that we observe is in multiples of E, okay? So there is no particle with 1.2 E, okay, or 2.6 E. It's always whole numbers times E. And what the property, like what we call that, is quantization. So we say that charge is quantized, okay, that it only appears in multiples, integer multiples of E. There's no fraction of E of a single particle in the observable universe. So another interesting fact, okay, protons and electrons, they have opposite signs, right? Protons we are calling positive, electrons we're calling negative, but in fact that's actually completely arbitrary. It's not really, they're not really negative or positive. They just display a behavior that we can assign the words negative and positive to, and it explains it well, okay? But they are not fundamentally negative or fundamentally positive. Really all they are is we know them by what we observe from them, which is that opposites attract and like repel. So Benjamin Franklin is actually the guy who decided this choice, that electrons would be negative and protons would be positive. And he didn't even know those existed at the time. He decided that by talking about this glass rod and silk, okay, because that's basically what those were the two objects that he used in his experiments in discovering properties of charge, as he used the silk on the glass rod. And that's kind of why that's the canonical example of demonstrating charge transfer. So let's get a little quantitative here, and let's bring back let's do an exercise, okay? We're going to bring back working with units, and we're going to work with some units you're familiar with, like mass, okay? And if you just took chemistry, you'll be familiar with counting how many electrons and protons are in a type of molecule and how many molecules make up an object of mass m, okay? And so in this example, we're going to determine how many, we're going to do that too. We're going to determine what the total charge is of all the electrons that are in a raindrop, okay? So we have a single raindrop, and we're told the radius of the raindrop. It's 1 times 10 to the minus 3 meters, and it's got a mass of 4.19 times 10 to the minus 6 kilograms. And the question is, what is the total charge of all the electrons in the raindrop? So one raindrop is made up of how many water molecules? Okay, that's the first question we need to figure out. And then from there, we know that each hydrogen contains 1 electron, and that oxygen contains 8 electrons. And so from there, we'll be able to figure out what the total charge is of all the electrons in all the molecules that make up that raindrop. So we need to figure out the mass of H2O, because we know the mass of the raindrop, right? The mass of the raindrop is this. So if we know the mass of one dihydrogen, one water molecule, we'll be able to figure out how many water molecules are in 4.19 times 10 to the minus 6 kilograms. So that's something that you can look up. And when you've done that, when you've looked up the mass of hydrogen times 2 and you've looked up the mass of oxygen, you'll see that dihydrogen monoxide has 2.99 times 10 to the minus 26 kilograms per molecule. Okay, so we divide the two to find out how many molecules there are. Turns out there's a lot. 1.4 times 10 to the 20 molecules of water in this raindrop. So now that we know there's that many molecules, how many electrons are in one molecule of water? Scroll back up, we figured that out. 1, 2, plus 8, that's 10. There's 10 electrons. So that means there's 10 times 1.4 times 10 to the 20 electrons in the raindrop. How much charge is in each electron? 1.602 times 10 to the minus 19 coulombs. So there we go. Multiply that all together right there. And when you multiply the number of electrons times the charge per electron, you get negative 224 coulombs. So that's a huge amount of charge, actually. It's a very big charge. So let's kind of put this to perspective here. So like, if there is 1.4 times 10 to the 21 electrons, how big is that? How many electrons is that? I mean, well, obviously it's enough to fit in a raindrop, okay? Well, the human body actually only contains about 10 to the 14 cells. So there's more electrons in that raindrop than there are cells in our body. And so, well, how is that possible? Remember that cells are, much, much bigger than electrons. Cells are essentially macroscopic structures compared to what an electron is, right? Cells are made up of tons of atoms, millions of atoms. So cells are much bigger than electrons. And that's why we, have a lot less cells than an electron does in a raindrop, or than a raindrop does have electrons. So let's look at this, got the concept. Okay, these are great. These are, another one of the many things that make up this slide deck, which is basically just, it's basically the e-text, right? It's basically the textbook in slide format. So these got the concepts appear in your book, and then they also appear in the slides. So let's go over them, and they're great study tools. I do pull, questions on the exam from Got the Concepts. Okay, they're not going to be identical, but I will test what this Got the Concept, maybe not this one specifically, but I will put on the test whatever this concept is testing. Okay, does that make sense? So let's do them. We're going to do them in class. That's what we do. So consider the rubber and glass rod, okay, in this figure here, part B of that bigger figure. Compared to their masses before they're rubbed with the fur and silk, what are their masses after being rubbed? Okay. So we know what happens to the charge, but what happens to the mass? Let's talk about what happens to the charge first. So you take the fur, you rub it with the rubber rod. What's left behind are a bunch of negative charges sitting on the surface of the rod. Okay? They've left the fur and gone to the rod. We just saw in the previous example that electrons have mass, right? Not a lot, but they have it. So now those electrons have left the fur and they're sitting on the rod. So the rubber rod has gained mass, right? What about the silk and the glass? This is what Benjamin Franklin was doing 400 years ago. No, 300 years ago. So maybe 200 years ago, 207. I can't do math. Not that kind of, not your math. Your math doesn't work for me. Doesn't work in my brain. So now in the case of the silk with the glass, right, we rub them together, and the glass, what's left behind is some positive charges. But remember that electrons are the mobile charges. They're the ones moving around. Okay, so what's happened is the electrons have left the glass and gone to the silk, leaving behind, an absence of negative charge, okay? An absence of an electron. So what that means, they didn't gain, so those aren't protons sitting there, right? Because where are the protons? They are trapped in the nucleus of an atom, and the only way we can unlock those is by blowing things up, okay? By adding a lot of energy, which we're actually getting really close to harnessing that as a source of energy for power plants. So, but anyway, what I'm trying to tell you is that these plus signs here are not protons. They are not positive charges. They are the absence of negative charges. And so therefore, glass is now missing some massive electrons and therefore has lost mass, okay? So the rubber rod, we're looking for, rubber rod has more, glass has less, and that's C. And then this is the explanation, okay? Charge transfer is the movement of electrons from one object to another. Okay, so wrapping up this section, we talked about charge. What is charge? Charge is a property of matter, okay? We say that electrons have negative charge, protons have positive charge. That's completely arbitrary, thanks to Benjamin Franklin. He's the one that decided that, but that's okay. We're going to stick with it. Charge is quantized, okay, meaning anything that has the property of charge is an integer multiple of E. And charge can be neither created nor destroyed. So charge, the conservation of charges is basically, that's what that is stating. It's the conservation of charge. Okay, it's a fundamental property of electrostatics. Finally, the last kind of concept, but we didn't really talk about it quantitatively, is that objects with net charge exert forces on each other, right? Either repulsion or repulsive charge forces or attractive forces. Okay? So in the next section, let's talk about types of materials, okay? We're going to talk about conductors and insulators. Those are types of materials, charged materials. And what differentiates those two types of materials is how free charges can flow. So the materials that we've talked about so far, the rubber, the fur, the glass, the silk, those are actually all insulators, okay? Insulators are materials where charges are not able to move freely. So you may be asking me, if charges can't move freely, why are we talking about the charges moving around? Well, there's like a hidden word in here, okay? They can't move freely within the material. Okay, there's kind of a hidden meaning there. They don't move freely within the material, but on the outside of the material, they can move around, right? So, and that's exactly what we saw, when I show you this example in real life, you'll see that. So charges transferred to an insulator, they'll stay. This is another property of insulators. if you transfer a charge to the outside of an insulator, it's gonna stay there, okay? Because it's kind of like locked into place until we do something to move it. And that something would be like rubbing it with a cloth, okay? There's also other ways we can transfer charges, but we're not gonna talk about that just yet. All right, so insulators, charges don't move freely within the insulator, but they can sit on the outside of the insulator and they will stay put on the insulator. Now, conductors. Conductors, we actually, use conductors all the time. We actually need conductors. We need them both, but we need conductors to charge our laptops, our iPads, our phones, right? We need charges to move freely in a conductor, to go from your plug, from your outlet to your computer, right? So conductors are materials in which charges can move freely within. So to illustrate the difference between how a conductor like copper behaves and how an insulator like rubber behaves, let's kind of do the same experiment where we take a special cloth and rub the rod of copper with it. In this case, we're going to use nylon for the same argument that its electronegativity is much different than copper. So we're going to rub the nylon on the copper, and what happens is the electrons will leave the copper and go to the nylon, and they will leave the nylon and go to the copper, obviously, right? What's left behind the nylon is the absence of negative charges, and where those negative charges went is to reside on the conductor, okay, on this conductor of copper. So this conductor of copper, this is where the difference happens between conductors and insulators. So on an insulator, the electrons will stick to the place that it was rubbed, okay? However, on a conductor where charges are allowed to freely move within the conductor, the electrons will redistribute themselves all over the surface of the copper rod. And so then you have the copper rod, both sides of it will have this attractive quality between it and the nylon rod, whereas the insulating rubber rod, it would only have this force of attraction on one side. Ions in an aqueous solution are conductors as well. And we know that water is really good at holding ions in solution because the water molecule has a slightly more negative charge on the side where the oxygen atom is and a slightly more positive charge on the side of it where the hydrogen atoms reside, right? It's a polar molecule. So an ionic compound like salt, sodium chloride, when it's dissolved in water, the positive ions will be attracted to the negative side of the water molecule, while the negative chloride ions would be hanging out and be attracted to the positive end of the water molecule where the hydrogens reside. And this is just another example of, it's a great example because our body is, mostly ionic solution, right? And cells use this ionic solution to communicate with other cells and communicate and do functions in the body. So it's a very interesting notion to look at the physics of conducting materials in the context of the human body. This is where it starts to get pretty interesting. So we're not going to get into this stuff too much, but it's really just there to show you that the physics that we're talking about here, it's not all about metals and electricity and things like that. There's a lot of biological aspects that are explained by physics, the physics that you're going to learn in this course. Let's look at this got the concept problem. I'm sorry that it's kind of cut off a little bit. I had some issues when I was recording this lecture initially, and so I'm doing a sound recording over what initially I had recorded. Anyway, let's get to it. In this conceptual problem, we have the normal sodium atom, right? It has 11 electrons, it's electrically neutral, but when it's in the compound of sodium chloride, the sodium atom actually has an ion, it is an ion, of charge positive E. How does the sodium ion acquire this charge of positive E? Well, the sodium ion, did it acquire this positive charge by A, annihilating one of its electrons, B, creating a new electron, C, transferring an electron, or acquiring an electron? I think we can already get rid of A and B because we remember earlier that charges cannot be created or destroyed, okay? So the sodium ion either acquired a positive charge E by transferring an electron to another atom or acquiring an electron. Well, part D doesn't make any sense either because if it acquired an electron, it would have more of a negative charge than it did before, right? It went from neutral to positive. It didn't go from neutral to negative, so we can eliminate D. And finally, the answer is part C. Transferring an electron to another atom. And which atom did it transfer it to? Well, the chloride ion, right? It gave its electron to the chloride ion, and that's why chloride is has a charge of minus E. Okay, so let's review this section. We learned that charges are free to move within a conductor. That's how we define conductors. But in an insulator, they are kind of locked into place. And in a metal conductor like copper, the moving charges are electrons. In a conductor such as an ionic aqueous solution, both positive and negative charges can be the moving charges, the charges that can be transferred around.